last lecture we were discussing the spectrum for a diatomic molecule, and due to the vibrational motion and rotational motion. So, we will continue our analysis of the diatomic molecule, and hopefully in this lecture we will also discuss the 3-dimensional oscillator. And after we finish that, that will be the end of simple solutions of the Schrodinger equation, and we will go over to the Bra and Ket algebra, which is due to the Nobel Prize winning physicist P.A.M. Dirac. So, today we continue our discussions on the diatomic molecule. In our last lecture, we had said that we have two atoms of a molecule, each one of mass m1 and one of mass m2. They are held together by a Hooke's law type force, and Re is the equilibrium distance, and the potential energy describing the interaction of the two atoms is assumed to be of the form of half k r minus Re square. Then we had solved the Schrodinger equation corresponding to that, corresponding to this variation of the potential energy distribution, and we had found that for small vibrations the total energy consisted of two parts, j into j plus 1 h cross square by 2 mu Re square. This is the rotational energy of the diatomic molecule plus V plus half h cross omega, where these are due to the vibrational energy, and the quantum numbers j is can take the values j equal to 0, 1, 2, 3, and the vibrational quantum number will also take values 0, 1, 2, 3. Actually, this is approximately equal to for small vibrations, but this is a fairly good description of the energy levels of as we will see for diatomic molecules. Now, here omega is the related to the force constant, Hooke's law type force constant k, by this relation, when mu is the reduced mass of the two particles. So, mu is equal to mu m1 m2 divided by m1 plus m2. As I had mentioned in my last lecture, in spectroscopy the energy levels are measured in wave number units, and it is represented, the energy is represented by the symbol E t, and this is defined as E by h c. So, if I substitute this here, so we will write, so let me write down this first, V plus half into G plus J into J plus 1 into B. So, here G, as you would guess, will be equal to h cross omega, this number, divided by h c. So, h cross is h over 2 pi. So, this is equal to omega by 2 pi c. And on the other hand, the rotational constant, this is known as the vibrational constant. This is known as the vibrational constant, and this is known as the rotational constant, and this will be equal to h cross square by h c. So, h cross square by 2 mu Re square divided by h c. So, if you write this down, so this is h over 2 pi, h square by 4 pi square. So, there is a factor of 8 one H cancels out with here. So, this will become H divided by 8 pi square C into mu R e square. So, this is the rotational constant. So, this is known as the, from the spectroscopic data, we will try to find both the rotational constant and the vibrational constant, and from there we will estimate the values of omega, k and the interatomic distance. So, this quantity capital B is known as the rotational constant. So, therefore, we rewrite this equation, we rewrite this expression for the energy levels for a diatomic molecule. So, T is equal to E by h c V plus half into G plus J into J plus 1 into B. Now, let us suppose the transition is made from V is equal to 1 and J is equal to J prime, and the transition is made to V is equal to 0 and J is equal to J prime plus 1. In fact, when a transition is made from one state to the other, the selection rule is that delta J could be either plus 1 or minus 1. So, you have from V equal to 1. So, the energy that is emitted is T 1 minus T 2, and that will be equal to V equal to 1 will be 1 plus half is 3 by 2 G plus J prime into J prime plus 1 minus, if V is 0, so that is half G minus, so this is minus the term value of the second term, that is from V equal to 1 and J is equal to J prime to V equal to 0 to J prime plus 1. So, this is the transition that I am talking about. So, this will be J prime plus 1 into J prime plus 1 plus 1, that is J prime plus 2. This will be here a B, here a B. So, 3 by 2 minus half becomes G. So, G. So, this will be minus, if I take J prime plus 1 common. So, this will be J prime plus 2 minus J prime. So, therefore, 2 will come out common. So, 2 into B. This is a very, these are the, so for this will become equal to, from J prime equal to 0 becomes G minus 2B. For J prime equal to 1, this becomes G minus 4B and G minus 6B. So, this leads to equally spaced lines, and the spacing between the two, lines in centimeter inverse will be 2B. The spacing between the lines will be 2B. These lines are referred to as the P branch of the spectrum. P branch of the spectrum. So, we will obtain equally spaced lines. Now, I will show you the experimental data in a moment, but before that let me consider the another transition, and the transition that we will be considering, that will be, instead of delta J equal to plus 1, we will consider delta J equal to minus 1. So, that let us consider a transition V equal to 1, J equal to J prime going over to V equal to 0, actually delta V is equal to plus 1. So, j is equal to j prime minus 1. So, if I do that, then it will be T 1 minus T 2 will be again 3 by 2 g plus j prime into j prime plus 1 b minus, and then V is equal to 0. So, half g and minus, so j prime minus 1. So, it will be j prime minus 1 into j prime minus 1 plus 1, that is j prime. So, if I calculate this, 3 by 2 minus half, 3 by 2 minus half will become g, and minus minus, so this will be plus, I am sorry. So, this will be j prime if I take outside. So, you will get j prime, and this will be j prime plus 1 minus j, this is a very trivial simple calculation, into b. So, the j prime cancel out. So, this as earlier. So, we will get 2, that is this will be g plus 2 j prime b. So, this will be for j prime equal to 1. So, j prime equal to 1 to j prime equal j equal to j prime to j equal to 0 transition. You will have g plus 2b. For j prime equal to 2, this will be g plus 4b and g plus 6b, and so on. So, once again we will obtain equally spaced lines, and on the either side of the value g. So, the difference between these two will be 2b. So, if I am now showing you the actual spectrum, the actual spectral lines. In the p branch, these are the observed lines, and the difference between these two are always 21.2 centimeter inverse, and this is the R branch. And as I had shown you earlier, that in the R branch we have g plus 2b, g plus 4b, g plus 6b. So, this is g plus 2b, this is g plus 4b and g plus 6b, and the difference between these two is 2b. So, 21.2 centimeter inverse. Let me show you the actual spectrum. This corresponds to the HCl. Actually, it is HCl 35 with the isotope which has a atomic mass of 35. So, these are the energy levels. So, this corresponds, the top diagram corresponds to V is equal to 1, the bottom diagram corresponds to V is equal to 0. This is V equal to 0, as I had tried to show. Now, you can see here that this line, this is j prime to j prime plus 1. This is a 4 to 5 transition, this is 2 to 4, 3 to 4 transition, 2 to 3 transition, and 1 to 2 transition, and 0 to 1. So, these transitions corresponds to j prime to j prime plus 1, and we have, this is in centimeter inverse, and the reciprocal wavelength is increasing in this direction, So, you will have, and similarly here also we will have V equal to 1 to 0, 1 to 0. So, but the lines, the absorption spectra are equally spaced, and that is what we have tried to show in the table, that this is the spectrum of the p branch and the r branch, and the difference between these two, difference in wave number units, difference in the wave number units between these two absorption lines, these are all equally spaced in the reciprocal wavelength space, and you will have the difference is always 21.2 centimeter inverse. And so, therefore, which validates the approximate theory that we have developed, and we therefore have this the 2b, we will find that 2b is therefore equal to 21.2 centimeter inverse. 2b is the separation between two consecutive lines, and we can see that they are consistently 21.2 centimeters, except at the center j prime equal to 0 to j double prime equal to 0, that transition is forbidden. So, at the center you will have the spacing, because you will have g plus 2b, g plus 4b, g plus 6b, and on the other side g minus 2b, g minus 4b, etc. But the g transition is not allowed. So, from this you will obtain that 2b is equal to 21.2 centimeter inverse. So, therefore, this implies that b is equal to 10.6 centimeter inverse, and therefore, for the HCl 35, the reduced mass is given by the mass of the hydrogen atom multiplied by the mass of the chlorine atom with the corresponding to the 35 isotope divided by MH plus MCl, and this will be approximately equal to 35 mH square divided by 36 mH, and if you substitute the mass of the hydrogen atom, so this will be 35 by 36 into 1.67 into 10 to the power of minus 24 grams, and if I evaluate this will come out to be about, you may write down 62 into 10 to the power of minus 24 grams. We are consistently working in the CGS system of units. So, as I had mentioned earlier that B, the rotational constant, is given by H over 8 pi square C mu R E square, and I know the value of H, which is about 6.6 into 10 to the power minus 27 erg second. C is about the velocity of light in free space, this is about 3 into 10 to the power of 10 centimeter per second. Mu we know, and the rotational constant we know, that is equal to 10.6. So, the only unknown is the interatomic distance, and that will, if you substitute this, it is a very simple algebra, this will come out to be 1.27 angstrom. Now, so this allows me that the interatomic spacing between the hydrogen atom and the chlorine atom in HCl 35 is about 1.27 angstrom. Secondly, we had shown that the spectral lines will correspond to G minus 2b, G minus 4b, etc. So, G minus 2b comes out to be 2969.9 centimeter inverse. You can, I had shown this, that this corresponds to G plus 2b, this corresponds to G minus 2b. In order to find the value of G, I can add these two and divide by 2, that is also possible, or I can just add 2b here. So, this corresponds to G minus 2b, this corresponds to G minus 4b, these are equally spaced spectral lines. This is G minus 6b, this is G minus 8b, and similarly here this is G plus 2b. So, I can add these two up and divide by 2, I will get G, or I can add 2b here and I will get the value of G. Let me add 2b there, does not matter, it is the same thing. So, 2b is 21.2. So, this is 21.2 centimeter inverse, and if I add this, so 999. So, this is the value of G. So, we assume that G is equal to 2991 centimeter inverse, and this was equal to omega by 2 pi c is equal to then 2991. So, this is G is equal to so much. We know the value of pi, we know the value of c, and from this we can easily calculate the value of omega, and the value of omega will be I leave it a very simple exercise, 5.63 into 10 to the power of 14 second inverse. And I already know the value of k. So, k, the force constant, is equal to mu omega square. You may recall that omega was equal to under root of k by mu. So, k is equal to mu omega square. I know the value of omega, I know the value of mu, and this comes out to be 5.14 into 10 to the power of 5 centimeter inverse. I am sorry, dynes per centimeter, dynes in the CGS system of units. This is the force constant, So, there are, before I proceed further, I must give the appropriate reference. This diagram, this actual spectrum, is adapted from a book on quantum physics by Eisberg, not Eisenberg, Eisberg and Resnick, and these data that I have taken, this is analyzed in our book on quantum mechanics by myself and Professor Lokanathan, and published by Macmillan and also Kluwer, but the actual data was taken from a very beautiful book by H.B. Dunford, Elements of Diatomic Molecular Spectra, published by Edison Wesley Publishing Company. So, the data is actually taken from H.B. Dunford's book. Now, the very fact that you have equally spaced lines proves the validity of our theory that the diatomic molecular spectra can be explained by assuming a simple Hooke's law type of force between the two atoms, and that the vibrational distance rho, you remember we defined the symbol rho for r minus Re, is the vibrational distance is small compared to Re. So, the very fact that we have been the experiment shows equally spaced lines for the diatomic molecular spectrum validates the theory that we have developed. I will give you one more example, and that is the so we have considered in this example the hydrogen chloride. This is the example that we have considered. We will consider one more example, and that is the carbon 12 O16, that is carbon monoxide. This is a molecule which consists of carbon, which corresponding to the isotope 12 mass number, and oxygen. Now, here also you obtain equally spaced lines. Here also, as I will show, this is also discussed in an example in our book by myself and Professor Lokanathan, and but the experimental data is actually of H.B. Dunford from Elements of Diatomic Molecular Spectrum, published by Edison Wesley Publishing. So, here also, as you will see, you will obtain equally spaced lines equally spaced lines. This is the p branch, this is the p branch of the spectrum, and this is the r branch, and the energy difference is equal, which once again validates our theory. So, this difference, so this is equal to g minus 2b, this is g minus 4b, and g minus 6b, and g minus 8b. I hope you understand what I am trying to say. So, each line is separated from the adjacent line by 2b. So, this quantity is equal to 2b. So, from here from this data we get that since they are equally spaced lines, that 2b is equal to 3.86 centimeter inverse. So, once again the very fact that you obtain equally spaced spectral lines validates the model that we have developed, and from this now we can find out once again the interatomic spacing. So, 2b is equal to 3.86 centimeter inverse, and therefore, this implies that b is equal to 1.93 centimeter inverse, and you have the reduced mass is mass of the carbon atom, mass of the oxygen atom, it is not 0, it is O, and then mass of the carbon atom plus mass of the oxygen atom. If you substitute these masses, then this comes out to be about 1.145 into 10 to the power of minus 23 grams. So, the rotational constant comes out to be is equal to h by 8 pi square c mu r e square, and you will obtain this as equal to 1.93 centimeter inverse, and I know here h, I know c, I know mu, from which I will get R e is equal to 1.13 angstrom. And similarly, since 2b is 3.86, so this is 2166.35. So, g minus 2b is equal to 2166.35. So, 2b is 3.86. So, therefore, g will be equal to plus 3.86. So, if we add this 20721. So, g will be equal to, so for this molecule, the quantity g will be equal to 2170.2 centimeter inverse, and we know the reduced mass. I leave it as an exercise for you to calculate omega. From this is g is equal to omega by 2 pi c. So, I can calculate what is omega, and then I can also calculate what is the force constant which are holding the two atoms together. So, that completes. I have given you two examples, one corresponding to hydrogen chloride, and actually the hydrogen chloride spectrum consists of two very closely spaced lines. If you look at this carefully, one line, if you can see this on the screen, one line corresponds to HCl 35, the other is of HCl 37. So, these are two isotopes of chlorine which are present in hydrogen chloride, which leads to two lines, two very closely spaced lines in the molecular spectrum. So, that completes the application of the solution of the Schrodinger equation to diatomic molecular spectrum. Now, this was one application, and the last application in the solution of the Schrodinger equation that we will be discussing is the three-dimensional harmonic oscillator, just oscillator. So, after this after we finish this, then we will start with the bracket algebra due to Dirac. So, in this we consider a two body interaction in which the potential energy distribution is given by half mu omega square. Mu is the reduced mass, omega is the natural frequency of the oscillator times r square. So, we would like to solve this 3-dimensional oscillator problem. You may recall that we had solved V of x is equal to half mu omega square x square. This we had solved. Now, there are two methods of solving this problem, and we will briefly discuss both of them. Actually, I will leave them as problems, and first I can convert this into Cartesian coordinates and solve by the method of separation of variables. And the second method will be, since it is a spherically symmetric potential, it depends only on the distance between the two particles, we can solve the Schrodinger equation as we have done for the hydrogen atom problem. We will briefly discuss both of them. So, let me first do the by writing it in Cartesian coordinates. So, in Cartesian coordinates m omega square, this becomes x square plus y square plus z square. Whenever the potential energy distribution is such that it can be written as some function of x plus function of y plus function of z, then you can use the method of separation of variables. Now, we will write v not as a function of r, but v as a function of x, y, z. So, the Schrodinger equation is del square psi plus 2 mu by h cross square E minus v. So, that is E minus v of x y z into psi is equal to 0. So, we will use first this representation, and therefore, we will use the Cartesian system of coordinates, that is delta 2 psi by delta x square plus delta 2 psi by delta y square plus delta 2 psi by delta z square plus 2 mu by h cross square E minus half mu omega square x square minus half mu omega square y square minus half mu omega square z square. Psi is equal to 0. Now, what we will do is, this is the standard method for separation of variables. By now, you should be all familiar with this, that psi of x, y, z, let us do this carefully. This I write down as a function of x times function of y times a function of z. I substitute this and divide by psi. So, I will get the first term, let me write it down. So, I have 1 over capital X y z. When I differentiate with respect to x, this can be taken outside. So, y z can be taken outside. So, this will become d2x by dx square. So, y z will cancel out. So, this will be 1 over x d2x by dx square. Similarly, when you substitute, this will give you 1 by y d2y by dy square. Similarly, this term will give me 1 by z d2z by dz square. And then I have divided by psi. So, this term will cancel out. I will obtain a term depending only on x, depending on y, and depending on z. And if you multiply this to this, you get mu square omega square by h cross square. Mu square omega square by h cross square. So, we have here if you let me do this carefully. So, we will have 1 over x d2 x by dx square, that is the first term, and if I multiply this to this, you will get mu square omega square by h cross square times x square plus a similar term for y, 1 over y d2y by dy square minus mu square omega square by h cross square y square plus another term for z, that is 1 over z d2z by dz square minus mu square omega square by h cross square z square. This must be equal to minus 2 mu e by h cross square. This I have taken to the right hand side, 2 mu e by h cross square. Now, you see, as we have done in the past, the variables have indeed separated out. We have used the method of separation of variables and the variables have indeed separated out. This, the first term, is a function of x only, this is a function of x, this is a function of y, and this is a function of z. And this added together gives me a constant. This can only happen if this is a constant, this is a constant, and this is a constant. This is how the method of separation of variables works. So, let me write this down as that this is equal to minus 2 mu E1 e by h cross square, just some constant, that mu is known, h cross is known, E1 is another constant, and this is minus 2 mu E2 by h cross square, this is minus 2 mu E2 E3 by h cross square. So, once again I use the method of separation of variables, that is, I wrote the wave function of x, function of y, and function of z. I substituted in the Schrodinger equation and manipulated it, and I find there are 3 terms. The first term depends only on the x coordinate, the second term depends only on the y coordinate, and the third term depends only on the z coordinate. Now, these 3 added together must be equal to a constant. A function of x, when multiplied by function added to a function of y and added to another function of z, can never be equal to a constant unless each one of them is a constant. So, we set this equal to minus 2 mu, we can set this equal to k1, and that I write as minus 2 mu E1 by h cross square. This I write as minus 2 mu E2 by h cross square, and this I write as k3, which is equal to minus 2 mu E3 by h cross square. So, you will have E 2 mu by h cross square, E1 plus E2 plus E3, that is the left hand side, will be equal to, with a negative sign, will be equal to minus 2 mu E by h cross square. So, this will give me E will be equal to E1 plus E2 plus E3. Now, let me write down the equation determining equation involving x. So, I will have 1 by capital X, please see this carefully, d2 x by dx square minus mu square omega square by h cross square x square is equal to 2 mu E 1 by h cross square with a minus sign. So, I rearrange this. So, I will get d 2 x by d x square plus, if I take 2 mu by h cross square outside, then you will have E 1 minus half mu omega square x square x of x. This is the one dimensional harmonic oscillator problem, and we had solved that in great detail, and we had found that E 1 was equal to n plus half h cross omega. Actually, I will put a subscript n 1, and n 1 will be equal to 0, 1, 2, 3, etc. And x of x will be equal to x of x corresponding to each value of n. We had found that out is equal to n n's of n h n of xi e to the power of minus half xi square, where xi is equal to gamma x and gamma was equal to mu omega by h cross. So, now I have solved the problem. E 1 is equal to so much, E 2 will be a similar expression, and E 3 will be a similar expression. So, the total energy we have got will be the sum of individual energies, and the total wave function will be product of the Hermite Gauss functions. So, we have solved the problem corresponding to the 3-dimensional oscillator. So, for this problem, we had started out with V of x is equal to so much. The solution of this equation, that is what we have been wanting to find out. We will find that the total energy will be n 1 plus half h cross omega plus n 2 plus half h cross omega plus n 3 plus half h cross omega. So, I can write this down as n 1 plus n 2 plus n 3 plus 3 by 2 h cross omega, where n 1, n 2 and n 3, each one of them can independently take values 0, 1, 2, 3, etc. So, this is the eigenvalues of the problem. So, I write E, which depends on 3 quantum numbers, n 1, n 2, n 3. And one can now see that the ground state energy eigenvalue, will be 0, 0, 0. So, 3 by 2 h cross omega. The first excited state will be either 1, 0, 0 or 0, 1, 0 or 0, 0, 1. So, 1 plus 3 by 2 is 5 by 2 h cross omega, and this will be 3-fold degenerate. There will be 3 independent eigenfunctions corresponding to this. Then you have, please see, 1, 1, 0, 1, 0, 1, 0, 1, 1, and then 2, 0, 0, 0, 2, 0, 0 0 2, all of them will have the eigenvalue 1 plus 1 is 2, 2 plus 3 by 2 is 7 by 2 h cross omega. So, that will be a 6-fold degenerate state, because there are 6 sets of quantum numbers which will give rise to the same eigenvalue E. And what will be my eigenfunction? So, let me write it down. The eigenfunctions, as I had told you, that psi of x, y, z, the eigenvalues add up and the eigenfunctions will be product x of x, y of y and z of z. And so, therefore, this will be n's of n 1 h n 1 xi e to the power of minus half xi square and then this will be n's of n 2 h n 2 of eta e to the power of minus half eta square multiplied by n's of n 3 h n 3 zeta e to the power of minus half zeta square, where xi is equal to gamma x, eta is equal to gamma y and zeta is equal to gamma z. So, these are the rigorously correct normalized eigenfunctions, orthonormal eigenfunctions for the 3-dimensional oscillator problem. That is, for V of x given by this, these are the eigenvalues. So, here this, so let me write it down once again. So, we will have for the ground state, n 1 is 0, n 2 is 0, n 3 is 0. So, the total energy is 3 by 2 h cross omega, and you have the equation psi 0 comma 0 comma 0. Then you have the first excited state. So, you will have state, you will have E is equal to 1 0 0, that is 5 by 2 h cross omega, and there will be 3 wave functions 1 0 0 0 1 0 and 0 0 1. The second excited state will have 6 eigenfunctions, and this will be 2 plus 0 plus 0, that is 7 by 2 h cross omega, and so this will be psi 1 1 0, psi 1 0 1, psi 0 1 1, and then you will have psi 2 0 0, psi 0 2 0, psi 0 0 2. There will be 6 wave functions. There will be 3 wave functions here and 1 wave functions here. So, these are the values of n 1, n 2 and n 3. So, let me write down just any one. So, let me write down for this. So, what will be psi 1 0 1? So, that will be is equal to, so let me write it down. So, ends of 1 h1 of xi, and I can take the exponential outside, ends of 2, n2 is 0. So, n0 h0 of xi, and then n1 eta, eta, and n1 h1 of zeta multiplied by e to the power of minus half xi square plus eta square plus zeta square. So, let me write it down in expansion. So, this will be equal to n1 n2, these are just normalization constant. h1 of xi is 2 xi, h0 of eta is 1, and h1 of zeta is equal to 2 zeta. So, this will be e to the power of minus half xi square plus eta square plus zeta square. So, if you write down in terms of x, y, z, so this will be 4 gamma square. So, n1, n2, n3 I write as n. So, 4 gamma square x y times e to the power of minus half gamma square x square plus y square plus z square. So, r square. So, you can write this in terms of, because it is a spherical asymmetric potential, you will have n into 4 gamma square, x as you all know is r sin theta cos phi, and y is r sin theta sin phi multiplied by e to the power of minus half gamma square r square. So, I have written this also, if I rearrange this. So, I will get sin square theta sin phi cos phi and then r square e to the power of minus half gamma square r square. So, it is a function of r, theta and phi also, as we should have expected, because after all it is a spherical symmetric potential. You can write the solutions as a function of r times YLM theta phi, and this is what we will indeed do in my next lecture. So, you can do it either with the spherical polar coordinates or with the Cartesian coordinates. It so happens that the Cartesian coordinates is little easier in this particular case, and in fact, you can generalize. I leave it as an exercise for you to work out the solutions for not the isotropic oscillator, like this: half mu omega 1 square x square plus omega 2 square y square plus omega 3 square z square. So, it is not an isotropic oscillator. So, in this case also I can write the solution as capital X, capital Y, capital Z, and separate the variables. Once the variables have separated out, I can write the solutions as a product of functions which depend on x, y and z. Since I cannot write this function as v of r, I cannot write this. So, we cannot then use the spherical polar, we cannot solve the Schrodinger equation in spherical polar coordinates. In the beginning of the next lecture, we will solve this Schrodinger equation for the 3-dimensional oscillator we will work out the solutions for an isotropic oscillator using spherical polar coordinates. Thank you.